14 billion light-years from Earth, something impossibly massive tears at the fabric of spacetime itself. TON 618 burns with the light of 100 trillion suns, a beacon so powerful it could be seen from the edge of the observable universe. At its heart sits a black hole so enormous that our entire solar system would vanish into its event horizon like a grain of sand dropping into an ocean. The numbers strain comprehension: 66 billion solar masses, an event horizon stretching 400 billion kilometers across. A gravitational pull so intense, it bends the very laws of physics around it. Yet the most disturbing aspect of TON 618 isn't its size. It's that, according to our best understanding of cosmic evolution, it shouldn't exist at all. The story begins unremarkably in 1957, when astronomers cataloging the northern sky noted what appeared to be a faint blue star. Nothing about it suggested the cosmic leviathan lurking behind that dim point of light. For years, TON 618 sat in observational records as a curiosity, one data point among thousands. Only when spectroscopic analysis became sophisticated enough to examine its light in detail did the truth emerge. Those spectral lines, stretched and shifted by the expansion of the universe itself, told a different story entirely. This was no nearby star. TON 618 was the blazing core of a galaxy from the dawn of time, powered by gravitational forces that would have seemed like science fiction just decades earlier. The light we see from TON 618 today began its journey across the cosmos when the universe was barely 3 billion years old, less than a quarter of its current age. The photons streaming into our telescopes are fossils, carrying information about conditions that existed when the first galaxies were still taking shape. We see TON 618 not as it is, but as it was in an epoch so remote that Earth, our Sun, and everything familiar in our cosmic neighborhood didn't yet exist. TON 618 reveals itself through violence. Supermassive black holes, the gravitational anchors at the centers of most large galaxies, spend much of their time dormant. Sagittarius A star, the 4 million solar mass black hole at the heart of our own Milky Way, feeds quietly, growing imperceptibly. But TON 618 belongs to an earlier, more chaotic era. As a quasar, a quasi-stellar radio source, it represents a supermassive black hole in a state of ravenous consumption. Matter spiraling toward TON 618's event horizon doesn't simply disappear. It forms an accretion disk, a maelstrom of superheated gas and dust rotating at relativistic speeds. Friction within this disk generates temperatures reaching millions of degrees. The disk doesn't just glow, it screams electromagnetic radiation across every wavelength, from radio waves to X-rays. This radiation pressure is so intense it can halt further in falling matter, creating a temporary limit on how fast the black hole can grow. Yet somehow, TON 618 has grown to a scale that defies these natural constraints. The accretion disk tells only part of the story. Perpendicular to the disk, TON 618 launches jets of plasma at speeds approaching light itself. These relativistic jets, powered by the black hole's rotation and intense magnetic fields, extend for hundreds of thousands of light years into intergalactic space. When these jets collide with surrounding gas, they trigger shockwaves that can compress material and spark new generations of star formation, or blast it away entirely, sterilizing vast regions of space. The black hole shapes its host galaxy through both creation and destruction. Consider TON 618 not in the distant universe, but at the center of our galaxy, replacing the relatively modest Sagittarius A star. The night sky we know would cease to exist. TON 618's luminosity would overwhelm every star in the Milky Way combined. Even at a distance of 26,000 light years, our actual distance from the galactic center, the quasar would appear brighter than the full moon, a permanent, unchanging beacon rendering stars invisible. The romantic darkness of night would become a memory. Astronomers would struggle to observe anything beyond the overwhelming glare of our own galactic core. The gravitational effects would be equally profound. While gravity falls off with distance, preventing TON 618 from immediately disrupting stellar orbits throughout the galaxy, the intense radiation would be lethal. High-energy photons and charged particles streaming from the accretion disk would sterilize any planets within thousands of light years. The habitable zones around stars would shift or vanish entirely as stellar atmospheres were stripped away by the quasar's wind. Life as we know it would be impossible anywhere near such an object. TON 618's event horizon spans approximately 400 billion kilometers. To grasp this scale, if you placed the Sun at the center of this black hole, the event horizon would extend well beyond Neptune's orbit, nearly reaching the Kuiper Belt. The entire planetary system, from Mercury's scorched surface to the icy reaches where comets drift, would lie within the point of no return. The mass required to generate such an event horizon, 66 billion times that of our Sun, creates gravitational effects that push physics into extreme regimes. At the event horizon, space-time curvature becomes so severe that light traveling at the universe's speed limit cannot escape. Just outside the horizon, photons can orbit the black hole in a region called the photon sphere. An observer at this distance would see the back of their own head as light completed circular paths around the black hole. Move farther out, and you encounter the innermost stable circular orbit, the closest distance at which matter can orbit without inevitably spiraling inward. For a non-rotating black hole, this occurs at 3 times the Schwarzschild radius. For TON 618, likely spinning rapidly due to its feeding history, the dynamics become more complex. The black hole drags space-time itself into rotation, a phenomenon called frame dragging, making certain orbits possible that would be impossible around a non-rotating black hole. The true mystery of TON 618 isn't its current state, but its existence at all. Supermassive black holes grow through 2 primary mechanisms: accretion of matter and mergers with other black holes. Both processes take time. Accretion is limited by radiation pressure. As matter heats up while falling toward the event horizon, it radiates energy that pushes against additional infalling material. This creates what's known as the Eddington limit, a theoretical maximum rate at which a black hole can grow by accretion. Even feeding at the Eddington limit continuously, a black hole starting from stellar mass, tens of solar masses, cannot reach 66 billion solar masses in just 3 billion years. The mathematics simply don't work. This suggests several possibilities, each with profound implications. Perhaps TON 618 didn't start from a stellar mass seed, but from a direct collapse of primordial gas clouds, creating an intermediate mass black hole of thousands or even millions of solar masses from the beginning. Perhaps the early universe provided more efficient feeding mechanisms we don't yet understand, allowing super-Eddington accretion under conditions that no longer exist. Or perhaps multiple large black holes merged in rapid succession, each merger adding mass without the gradual accumulation bottleneck. None of these explanations fully satisfies. Direct collapse requires extraordinarily specific conditions. Super-Eddington accretion would require the black hole to somehow overcome the very radiation that limits its growth. And while mergers can add mass quickly, they require multiple massive black holes to exist in close proximity, merely pushing the problem back one step. Where did those massive progenitors come from? TON 618 and quasars like it function as cosmic time machines. The light we observe has traveled for billions of years, carrying information encoded at the moment of emission. Spectroscopic analysis reveals absorption lines corresponding to elements in the intergalactic gas clouds the light passed through. These signatures map the distribution and chemistry of matter throughout cosmic history, showing how the universe evolved from the simple hydrogen and helium produced in the Big Bang to the rich periodic table that makes planets and life possible. Quasars also serve as calibration points for cosmic distances and expansion rates. Their extreme luminosity makes them visible across vast distances, and their spectra provide redshift measurements that quantify how much the universe has expanded since the light was emitted. By comparing different quasars at different distances, astronomers trace the expansion history of the universe and test models of dark energy. The influence of quasars on their host galaxies extends beyond immediate destruction. The energy output regulates star formation across the entire galaxy. Too much quasar activity, and the gas needed for new stars gets blown away or heated beyond the point where it can collapse. Too little, and galaxies would form stars too efficiently, exhausting their fuel too quickly. Observations suggest a correlation between supermassive black hole mass and the properties of galactic bulges, hinting at a deep connection between the largest structures and the smallest singularities. TON 618 represents an extreme, but it's not unique. Astronomers have discovered other ultra-massive black holes in the early universe, each posing similar questions about rapid growth and cosmic infancy. These discoveries force revisions to models of galaxy formation and black hole evolution. The universe, in its first billion years, was stranger, more violent, and more conducive to extreme growth than current theories predicted. What remains unknown exceeds what we've learned. The exact mechanisms that allowed such rapid growth remain speculative. The internal structure beyond the event horizon, the nature of the singularity itself, lies beyond observational reach and perhaps beyond the reach of physics as currently understood. General relativity predicts a point of infinite density, but quantum mechanics suggests this prediction breaks down at the smallest scales. What actually exists at the core of TON 618, beneath billions of solar masses of warped spacetime, may require a theory of quantum gravity we haven't yet developed. TON 618 sits in our observations as a monument to the extremes the universe permits, a reminder that the cosmos operates on scales and with mechanisms that dwarf human intuition. It shines from the deep past, its light a message from an era when the universe was young and wild, when black holes could grow to impossible sizes in impossible time. The monster that shouldn't exist does exist, forcing us to revise our understanding of what the universe allows and what darkness lies at the heart of light.